think about how the signaling works and the timing, well, the important edge of the clock is the rising clock edge. So instead of drawing a square wave, I've actually just drawn up arrows to indicate when the clock goes high, because that's when the state register basically changes its value. And you can see that here. Shortly after the rising edge of the clock, a new state is available on the S state wires, and they come out. They then go through the ROM, and one of the jobs of the ROM is to compute this next state. And that has to happen with enough setup time, so before the next rising edge of the clock, the next state has been stable for the setup time of the register before the rising edge of the clock happens. And then at the next clock edge, that new state becomes the current state. So this notion of you're in a current state, you're computing a new state, at the next clock edge you transition to that new state. So there's a sequence of states that you're going through, which corresponds to making the elevator service the right person on the floor, or transmitting a convolutional code from the Cassini spacecraft back to JPL. I mean, pretty much anything in life that's sort of, quote, interesting, involves a certain amount of having to sequence through a set of operations. Your computer, of course, is a giant sequential machine. And in fact, the sequence of states that it goes through is a sequence that we program. And we're going to be talking about programmable state machines in the lectures to come. So we're sort of on the stepping stones bringing us to a true programmable computer. Okay. Now, if you have a megahertz clock and you're putting your fat finger on the button, you're not going to be able to, you're going to sit there with your finger on the button for what might be many clock edges. And one of the things that we can do is we can adjust our state machine so that, in fact, when you press the button, you go into a particular state, and it's when you release it, when the machine finally detects on a particular clock edge when you've released it, that's when you make the transition. So rather than holding it down and saying, oh my God, the guy has just entered 7.2 million zeros, right, because he held the finger down for 7 seconds on the button, what we're going to do instead is process. We're going to add some additional states to help us process the fact that when you push a button, first the contact closes and then it opens. And so we're going to account for that in our state machine. Now the little guy over here in the corner actually has identified a sticky wicket. I'm walking up to this combinational lock outside of one of the rooms in Stata, and I'm putting, right here in the 004 lab, and I put my finger on the button. It's not like I've suddenly looked over to see what the clock image is on the wall and said, wait, I have to wait just to the right moment so I don't violate the dynamic discipline. Right? I have no knowledge of the clock. So in general, processing information from the real world into these clock synchronous circuits raises the potential of violating our dynamic discipline, violating the setup and hold times for this register here. And that's a real problem, and one that we'll devote a whole lecture to on Thursday. But for now, let's not worry about it. How many states are there in this state machine? Say, look, here's a picture, here's a hardware circuit that I claim is an FSM. Can you tell me something about how many states it has? Yes. It has at most 2 to the k. It might have fewer, but it has 2 to the k. Everybody happy with where 2 to the k came from? Those correspond to the 2 to the k combinations that I can get on the k state bits. A different encoding for each state that I'm in. Okay, suppose I put 2 state machines in sequence and I draw a big dotted line around that combo and say, that's a state machine. How many states does it have? Well, be brave. Make a wild guess. There's only so many things I can do with m and n. So m times n. Okay, and I think that's right, because without any other information, each of these machines may independently be following its own sequence of states. And in fact, for every state that the first machine is in, I might be in any one of n of the states in the second machine. Now, it may be that I'll provide you more information that shows how the states are related, and now that may be much smaller. But in the absence of that, okay, here's a really interesting thing. Okay, here's an FSM. Can you discover its rules? If I put a box on the table that has some buttons and a light that goes on occasionally, can you show me the state transition diagram for what's inside? Okay, the consensus seems to be no. Okay, and that's wise of you, particularly if you've looked to the next slide. The answer is no. Okay, and the reason is you can never, without any bound on the number of states, you can't be sure whether you've explored all the behaviors that are hidden in the transition diagram. So you might press 0 and 1 and say here I'm going to press 0 for a while and nothing happens. I press 1, the light goes on. I keep pressing 1, the light stays on. I press 0, that's fine. And I press 2 1s and 3 1s. And I'm pretty convinced that 1 turns it on and 0 turns it off. But what's inside the machine may, in fact, if you pressed your 17th one, is when the light suddenly goes off again. So without any bound on the number of states, I cannot exhaustively enumerate all the possibilities because I don't know how long I need to keep going. Everybody with me on that? If you do have a bound on the state, and there's 2 to the k maximum states that you have, then you can go back and you can say, if I press 1 2 to the k times, okay, and then I wait and the light still stays on, I can say, okay, I think I'm pretty clear now that there isn't one of these gotchas at the end of one of these chains. So with the bound or the number of the states, you can do that. What about these two machines? They're clearly different. They have different arcs, different circles. I mean, one's a lot bigger than the other. Are they different? Okay, everybody's sort of shaking their head no. And what you're doing is you're looking beyond the superficial, arcs and arrows, and you're sort of saying, behaviorally, there's no way to distinguish them. No combination of zeros and ones will distinguish the diagram on the left from the diagram on the right. Right? So these are functionally equivalent, which means that if I had a choice of which one to build, I'd probably build this one because a 2-state machine will be cheaper in terms of the logic than that 5-state machine. Everybody happy with that? So there's this notion of equivalence.